All right, so this is essay question 2 for unit 4. And in this part, we're talking about the lungs. So I'm not gonna go over a ton the anatomy, but we have our lung here. This is supposed to be alveoli, but I just drew it big. But yeah, something about the lungs, it's super dependent on pressure. And so we're gonna be talking a lot about pressure and how that pressure can drive gas exchange, but also how the pressure can, how that functions to open and kind of close the lung for ventilation. But first right here, we're going to talk kind of about the membranes and the pleura of the lung. So yeah, this black line right here is the actual lung, the lung tissue. This green line I drew, that's called the visceral pleura. And then we have the parietal pleura, that's the blue line on the outside. And the way I kind of like to remember visceral pleura, parietal pleura is P for parietal is like P for parent, and parents like to surround their children, like to keep them safe. And so parietal pleura is going to be on the outside, inside is going to be the visceral pleura. And in between those two, we have the pleural cavity. And outside of the parietal pleura, we have the thoracic wall. Right here, I drew the ribs to represent that. But all that's gonna be interrelated for expanding our chest wall and creating differences in pressure to expand and close the lung. So I'm trying to think what I want to talk about next. Let's see. Let's talk about inhalation and exhalation. Inhalation, the muscles that are used are like the diaphragm. We use the sternocleidomastoid. We use the scalene muscles. Those are more found kind of at the top up here around the neck and are connected to, I don't know exactly what this part is, I can't remember, but just the bones right here, kind of like the ribs and stuff like that. And as we breathe, it kind of helps bring it up, kind of helps open it. And then also for when we inhale, I'm trying to remember, I think it's the external intercostals, and those kind of help expand, lift out, open up the thoracic cavity. And something that's important to talk about, I'm talking a lot about expanding the area, and we're talking about pressures. And the law that involves that is Boyle's law. And Boyle's law pretty much is the relationship between volume and pressure. So if we have an area of higher volume, that means we're going to have a decreased pressure. And the way you can think about that working is if, let me think. Now we'll talk about a balloon. So if you have a balloon and you blow it up, it has a big area and the pressure is low because it's expanded. So we have volume big, pressure is low. But if you take that balloon and you try to squish it down, you're decreasing the volume, you're pushing it together, what's gonna happen? It's gonna pop. And the reason why it pops is because pressure went up so much. The material of the balloon wasn't strong enough to hold that or support that increase in pressure, so it popped. And so it's the same thing within the lungs. That's why volume and pressure is so important. And so let's kind of draw kind of what it looks like when we exhale. Before I do that, in the pleural cavity, there's a fluid that is in between the parietal pleura and the visceral pleura. And I think it's just called, what's it, like pleural fluid? Can't remember the exact name of it, but it's just a fluid. And it acts as a lubricant because when you're breathing in and out, these two, the parietal and the visceral pleura are both rubbing together. And so we don't want a lot of friction. And so that's why in this cavity, we have a fluid that decreases that friction. So it's not a lot of wear and tear and it doesn't break down. And so, I think, is there anything else I want to mention? But yeah, in reality, these two, there's really not a lot of space. They're really pretty much right on top of each other. And the only thing separating is a thin layer of that fluid. And then yeah, we'll just stop right there. But let's look at this. Let me grab a red marker real quick. So we're talking about the diaphragm, and let's just say the diaphragm's right here. The diaphragm moves down. What's happening in the thoracic cavity? As it moves down, the volume's increasing. So there's a decrease in pressure. And that decrease, and also, as well, when we're breathing, we talked about the scalenes and the sternocleidomastoid. But the actual chest wall is also expanding, creating more volume. And so that's going to decrease the pressure, which is then going to allow the parietal pleura to expand. And these two, since they're so close together and they have this liquid, it's almost like they're connected. They have a force that's pulling them together. And so they're very kind of connected, even though they're not connected with this fluid there. It's almost as if they're connected. And so when a force pulls on the parietal pleura, it also pulls the visceral pleura as well. And so then the visceral pleura will pull out, and eventually it's creating this negative pressure. The lung's going to expand because it's like kind of being vacuumed. This negative pressure is pulling on the lung to expand and to open. That's what happens when we breathe. Diaphragm goes down, the space in our thoracic cavity gets bigger, so pressure goes down. We get a negative pressure, or it's always negative pressure, but it gets more negative, and then it pulls on the lungs to expand them. And so yeah. And then with the opposite, we have diaphragm relaxes. It's pushing up. All these are pushing back. These are relaxing. Oh yeah, and with exhalation, that's more of a passive. At resting, that's a passive. It's passive. There's not really any muscles involved in that besides the diaphragm relaxing, but it's not like it's really flexing to relax. It's just relaxing. So our area gets smaller. Here where our negative pressure is in the pleural, can't remember, is it the, trying to remember. Yeah, the pleural pressure. The pleural pressure is decreasing in the pleural cavity because this in the thoracic cavity is decreasing. The pressure is becoming more positive or less negative, and it's going to cause this to, the lung to, I don't know what the word for it is, but it's not going to expand, it's going to decrease in volume. But also too, something I forgot to mention, when this is happening, it's also having an effect on the alveoli, because the alveoli, they're also sensitive to this pressure as well. So when we're expanding and the lung expands, it's also going to expand the alveoli. And when the lung, when the volume of the lung decreases, it's also going to decrease the volume of the alveoli as well. And kind of like the average pressure within the alveoli is -1. This marker is not very good. -1 to like -3. And this is kind of in comparison to the pressure outside. The pressure in the atmosphere, it's 760 at sea level, but for this we're just going to refer to it as 0. And then within the alveoli we have like -1, -3. And then in the pleural cavity, in the pleural pressure, that's -4 in this area. So it's always referred to as a negative pressure. That's how we expand the lungs. It's through a negative pressure, not a positive pressure. Positive pressure is if we had like somebody on a ventilator or a valve mask, a BVM, and we're forcefully pushing air into their lungs, that'd be positive pressure. The way we breathe normally is through negative pressure, which expands the lungs. And yeah, but with this, we have the alveoli where the air comes in or the gas comes in like CO2. And then we also have the blood, these capillaries that are running through, and there's gas exchange between the alveoli and the capillaries. And for this gas exchange to happen, it needs to be something that's small and not charged, and that's like CO2 and O2, they're gases. They can easily diffuse through the membrane. And the membrane that they're diffusing through, I have it written down here, within the alveoli, there's something called surfactant, there's water or a lot of moisture within the lungs, and so there's kind of a water that's built up around the alveoli. And so the CO2, when it's going into the capillary from the alveoli, has to pass through the kind of that aqueous solution, which I'm pretty sure it's just water, but it also has surfactant as well. But it passes through there. It passes through the squamous cell of the alveolus, passes through the alveolar basement membrane, and then it goes through the interstitial space in between the membrane of the alveolus and the membrane of the capillary, and then it hits the capillary basement membrane and then goes through the squamous cell, the capillary, or the endothelium. That's another thing I should probably mention. Within the alveolus, there's 2 types of cells. One of them is the type 1, the squamous cell, and that one's way more abundant. I think it's like high 90% is what the alveolus is made up of the squamous cell, the type 1, and that one's used for, like we just talked about, the gas exchange. But then we also have the type 2, and that one I think is like cuboidal cell, and that one's a lot less abundant, but what it does is it secretes surfactant, like we'll talk about this more in a minute, but there's this fluid or this moisture in the lungs, and it builds up around the surface of the alveoli, and it can cause the surface tension inside the alveoli to increase and make it to want to collapse more. And so to kind of combat that, the surfactant that is produced from these type 2 cells decreases the bonding of these water molecules to decrease the surface tension, which will put less kind of stress on the alveolus to collapse and allow it to be able to stay open more. Let's see, I drew this nice little graph from our book, and with this graph, it's pretty simple. Up here is talking about volume of the actual lung. Right here is talking about the partial pressure, not partial pressure, but the pressure within the alveoli, so the alveolar pressure. And then down here, and with the green line, that's representing the pleural pressure. And so like we talked about, is the pleural pressure is always more negative. I think it's usually around -4 or -4 less than the actual alveolar pressure. But it can differ. I think the range for the alveolar is like 1 to 3, and the range for the pleural pressure is like -4 to -8. And then remember the outside is, we have it at 0. But yeah, so for inspiration, that's when we breathe in. This is when so first it starts out with the pleural pressure, and the pleural pressure is going to drop. It's going to get down to around, let's say in this graph it's saying -6, but that's going to bring the alveoli pressure down, alveolar pressure down to about -1. But then when we start to exhale, this graph isn't perfect, but the pressure in the pleural pressure begins to increase, which then causes the alveolar pressure to increase, and we get about 0, where that's matching the atmospheric pressure. And we start to exhale once we get more of a positive pressure within the alveoli, and it causes, get to about +1, and that's what pushes the air out, because on the inside we have like a +1 and the outside is 0, so once we get positive out here, it's gonna go to, the gas is gonna go to an area of less pressure, which would be outside. But when we're inhaling, the area of less pressure is inside, so air is gonna come in, increase in volume. But then when the pressure on the inside becomes more positive than the outside, specifically in the alveolar pressure, it's going to push the air out, because the outside's 0, inside's +1, so it's going to push it out to an area of less pressure. So that's kind of that, understanding that graph. So that's all I want to talk about with that. Let's look over here. This right here is Boyle's law right at the top, but I have all the laws written over here more. We'll talk about them. But yeah, first we'll talk about Boyle's law. That's the relationship between volume and pressure. They're inversely related. But yeah, these are 3 graphs that we talked about in class and in the book. And they represent kind of a pressure volume. Lung volume over here, pressure on the bottom. And what this is saying, in a normal lung, this is kind of what it looks like graphical wise of when we inhale and exhale. So first we're going to inhale, and as you can see, there's kind of different slopes of this on this graph. This slope is less steep, and so it's showing, okay, it's taking more pressure to get a little bit of volume increase. But then right here, taking less pressure to get even more of a volume increase. And right here in the book, I think in class we talked about this, it's kind of topping it off, and so this is kind of where elastance is a problem. So we're really kind of, the lungs getting really stretched, and so to kind of overcome that high amount of elastance, it does take a little more pressure to get that last bit of volume. Don't know how important that is, but it is true. But with this, yeah, kind of what it's saying is, this is like the tension we have to overcome, because whose law is it? I think it's Laplace's law. Talks about radius and pressure relationship. So if we have a bigger radius, there's less pressure. If we have a smaller radius, there's greater pressure, and that's because there's surface tension that's involved. And so here, when the lung or the alveoli are smallest, it takes a lot of pressure to overcome that small radius, and also there's a greater amount of surface tension because that water is concentrated within, so there's greater amount of surface tension, there's greater pull from those water molecules, and so it takes a greater amount of pressure to overcome that surface tension and that small radius. But then we get it big enough to where it's not really a problem anymore, we get that big increase in volume, and then up here we kind of talked more about to do with elastance. So that's a normal lung. Here we have different lung diseases. Some are restrictive, some are obstructive. Restrictive has more to do with difficulty breathing in. And so there's less lung compliance. It's harder to breathe in. That can be due to like buildup of scar tissue on the lungs, different things. That's all I can really remember. But this is what we see a lot with, I believe it's with, is it with smokers or no? I believe it's with smokers. Something called emphysema, if I'm remembering that right. But it's okay, it's not a huge deal. But this is someone with a restrictive lung disease where it's more difficult to breathe in, but they don't really have a hard time breathing out. And so right here, as you can see, just to get a little bit of volume, they have to do so much work. But then finally, they get that increase, but they can only, with the amount of pressure they can only have so much volume come in. So they have a lot less volume coming in per breath. Then it kind of just goes down and they're able to breathe out. And then with, this one's obstructive, COPD, and this is, you're okay breathing in, but it's a lot harder to breathe out. How's it going? You have a class in here?
No.
Oh, okay.
Am I?
You're fine to study. I'm just gonna do this video, so I'll just be talking, but yeah, you're good.
I'll be quiet.
No, you're good. It's just for an assignment, so it's not a big deal. And then for this part right here with obstructive lung disease, you have a lot harder of a time getting air out for exhalation. And so you're gonna have to recruit muscles to exhale. And the muscles that you'd recruit are the abdominal muscles and also I believe it's the internal intercostals that you have to recruit as well. So this one looks more like this, as you can see. To get volume, it takes a normal amount of pressure, but then to exhale, it takes a great amount of, let me see, I think it's pressure to, you have to exert a lot more to exhale or expire the air inside your lungs. And so it's kind of the importance with obstructive and restrictive. Something we talked about before, we talked about the pleural cavity and how it has pleural fluid inside. And the reason why that's important is because if you don't have that pleural fluid, there's something called pleuritis. And if we get an infection within the pleura, that can lead to either an excess fluid in the pleura, or it can lead to a decreased amount, I think. And pretty much what happens, I guess in this case with pleuritis, it's an excess amount of fluid. And with the visceral, remember on the inside and the parietal on the outside, those two layers get separated too far apart from each other. And like I talked about, they have a attraction towards each other when they're close together due to the fluid. When they get too far apart, they lose that attraction. And so when the thoracic cavity expands, the parietal pleura is not able to pull on the visceral pleura to help expand the lungs. And so when you lose that attraction, that's when you can have a collapsed lung. And so that's why the amount of fluid within the pleural cavity is so important. And then this last one right here, we're just gonna go over the laws. So we already talked about Boyle's law. That's the pressure-volume relationship. We have Laplace's law, which is the radius-pressure relationship. So a bigger radius is gonna be less pressure, and a smaller radius is going to be greater pressure. And that's important, we'll talk about it in a second, both the alveoli and the different sizes of the alveoli. Dalton's law and Henry's law, we'll talk about in a minute, but Dalton's is partial pressure, and then Henry's law is the solubility of gas in a liquid. But with Laplace's law, that brings us to surfactant, which is a very important contributor to our ventilation and our breathing. And so, like I mentioned, the alveoli, we have different sizes. We have some that are smaller and some that are bigger. With the bigger alveoli, since there's a bigger radius, there's less pressure within the bigger alveoli. And also there's less tension because if you remember, we talked about how we have, within the lungs, it's a lot more, what's the word? It's more humid. it's more moist, and so we have water that can build up on the surface of the alveoli. And because with the bigger alveoli, it's more spaced out, the water's not so concentrated on the surface. And what these water molecules will do is they're attracted to each other, and they want to kind of pull themselves together. And so as they're on the surface of the alveoli, they'll want to pull the surface of the alveoli inward to decrease the volume. But it's not that big of a deal with the large alveoli because they have a big radius, and also it kind of it decreases the concentration of the water on the surface, and so there's not much of tension as well. And so the big ones are okay, but they also have a risk of overexpansion, or they can burst or explode, so that's their kind of risk. But then with the smaller alveoli, they have a smaller radius, which is going to cause them to have a higher pressure. But then they also have with being smaller, they have a higher water concentration on the surface of the alveoli. So there's greater force kind of pulling it down together, pulling it to a smaller volume, which could lead to collapse. And so when the air comes in, and this is if we don't have surfactant, we talked about how the bigger alveoli are going to pretty much get all of the new air that comes in, all the fresh oxygen. And they're also going to be able to expel all of the CO2 that comes from the blood that we don't need. But then this smaller alveoli, it's going to have a greater pressure, and so none of the new air is going to go in there. So there's going to be no gas exchange, and it's not going to be doing anything to contribute. And so that's why it's important for surfactant. We talked about that being produced from the type 2 cuboidal cells. The type 2, I can't remember, it's just the type 2 cell of the alveoli. That one we said was a lot less abundant, but it's super important because it produces a surfactant. I can't remember exactly what it's made of, but I know it has a fatty tail. And that fatty tail, pretty much what it does is it disrupts the attraction of the water to want to pull the surface of the alveoli in to collapse. And so these will produce on the surface, and pretty much will just disrupt that surface tension to allow that alveoli to be able to stay open with less stress. And so once we have this surfactant, that's going to be found on big and small alveoli. But what it's going to do, it's going to kind of equalize the difference that the small alveoli and the big alveoli have. And so it equals it out, so when new air comes in with the surfactant, it's going to equally go into the big alveoli, and it's going to equally go into the small alveoli. So we have an equilibrium, which gives us more equal gas exchange. And also it decreases the risk of a bigger alveoli bursting, and it decreases the risk of a smaller alveoli collapsing. So surfactant is super important and contributing to that. On over here, we're going to talk about the alveolar gas exchange. And this is just an equation you can use, like we talked about in class, in like a clinical setting. And I can't remember why it's super important, but let's just kind of talk through it. So this first part, what it is, it's pressure in the partial pressure in the alveolus, and that equals, well, I guess that's important because we want to know how much pressure we have in the alveolus to see if we're having good gas exchange and good amount of oxygen coming in. That equals the partial pressure of the atmosphere, which is usually 0.21. That can be higher if someone's on supplemental oxygen, but that's pretty much just the amount of air that's coming in, or the partial pressure or the fraction pressure of oxygen in the atmosphere of the air coming into the lungs. And then we multiply that by taking the pressure in the atmosphere, which is 760, and we subtract that from the pressure of water, the water vapor pressure within the lungs, and that's 47. And we subtract those two and we multiply it by the fraction, 0.21. And then we take that number and we subtract that from the pressure of CO2, the arterial pressure of the CO2, divided by the R. I can't remember what the R is, but that's pretty much, yeah, I can't remember what that is, but that's going to usually be 0.85, and that is because that depends on our diet. And so if we have, I think it's a higher protein diet or a diet that's low in carbohydrates, that's going to be more like 1. But for a Western diet, like it said in the book, we can pretty much take that and call it 0.85, and that's kind of just the normal or the average. But the arterial pressure of CO2, that's 40. And so I'm just going to go through the example we did in class for this and get it pulled up. Okay. So this question in class was a 50-year-old smoker is evaluated for chronic emphysema. He's on supplemental oxygen that has increased his FiO2 to 29%. He's at sea level, and his PaO2 is 102. And so this pretty much we're just plugging it in and doing algebra. So let me get this to go straight. Okay. So we know the PaO2, the partial pressure in the alveolus. This gives us it here, it's 102. And that's going to equal the rest of our equation, which the fraction of O2 is it would be 0.21, but he's on supplemental oxygen, so that makes it 0.29. And then we're going to take that and multiply it with what's in these parentheses. They say he's at sea level, so it's going to be the 760. And we're going to subtract that from the vapor water pressure within the lungs, and that's 47. And then once we get that number, this is where we come over here, and we have the 0.85 on the bottom for the R. Let's see, 0.85. Then on top, that's what we're looking for. This is what we don't have, is the arterial pressure of the carbon dioxide, and we're trying to find that. So we'll just put X. And X is going to equal our PaCO2. So in this case, we're just going to do the math. So we get 760 minus 47. Oh, 760 minus 47. That equals 713. We're going to multiply that by 0.29. So we're going to take 0.29 times 713. That's going to give us 206. So kind of see what we have now. We have the 102 equals 206 minus X 0.85. Is there a class that's going to start here in a minute?
At 2, yes.
At 2, okay, sweet. I'm just finishing up a video for a class, so.
Fun stuff.
Yeah. And then, so we're going to take this part now, and we're going to subtract, let's see here. We're going to kind of flip it and make this positive. So we're going to get X over 0.85. And that's going to make this let's see, equals 206 minus 102. Let's see what that gets us. 206 minus 102 is 104. And we have to multiply that by 0.85. And that gives us 88.4. And that 88.4 is what the PaCO2 equals. And let's see what the question says. So it wants to know in the healthy individual with a FiO2 of 29%, would we expect the PaO2 to be close to the partial pressure of oxygen at atmosphere? And yes, that's correct. And then for number 2, his PCO2 is likely higher than 40. Could help explain why his PaO2 is different than what is expected. So this would be correct because we got his PaCO2 that's higher than 40. It's at 88.4. And then we'll just finish up with that. And so I have a few more things to cover. We'll do that in a different video. All right, so this is the last part of question 2 for unit 4. And we're gonna discuss, like it says here in red, discuss how CO2 and O2 are transported in the blood, and include a description of the oxygen hemoglobin dissociation curve and factors that influence the affinity of hemoglobin for oxygen. And how do these factors affect the oxygen hemoglobin dissociation curve? Okay, so, nope, where is it? Here we are. Okay, so the first one I want to talk about is how oxygen and CO2 is exchanged at the point of the alveoli into the capillaries on the alveoli within the lungs, and then how that how the blood transports these gases from the lungs to the heart, and then from the hearts to the tissue, or from the heart to the tissues, and then from the tissues back to the heart, back to the lungs, where the exchange happens again. So first I want to start out with inspired air. When we breathe in air, the partial pressure of O2 is going to be 160 for a healthy person, or I guess maybe not just for a healthy person, but also just for if we're just breathing room air. Someone who's on oxygen is going to obviously have a higher partial pressure of O2. And then the partial pressure of CO2 in the air is 0.3, so it's super low. It's pretty much just negligible. And let's look at, okay, so we have the alveoli, and that's where the air comes in, and this is where the gases are, and then they're exchanged, like we talked about, through the membrane of the alveoli to the capillary of the blood vessel that's surrounding the alveoli. So here, when oxygen comes in, when air comes in, the partial pressure of the oxygen in the actual alveoli is going to be 104. And the reason why that is, I can't remember 100%, but I think just as it comes down, it's coming down the trachea and the bronchi and the bronchioles. It's getting affected by, I think, the partial pressure or the hydropressure of water. So pretty much just in the lungs, we talked about before, there's moisture, and the temperature within the lungs is actually kind of high to where that moisture inside, I can't remember how much of it, but a good amount of it is gas. And so that's going to affect the partial pressure. So that's why we go from 160, then we get down to the bottom in the alveoli, and we have that 104. And then for the partial pressure for CO2 is at 40. And so when we have, on this side over here where it's blue, we have deoxygenated blood coming from the venous side, and it's coming from the right right ventricle, and it comes into the lungs, and the blood that's coming, the deoxygenated blood, its partial pressure for oxygen is 40, and then its partial pressure for CO2 is 45. And we know that gas is going to follow pressure gradient, and so it's going to go from high to low. So the oxygen is going to go from 104, and inside the blood it's 40, so it's going to have a high pressure gradient to move down into the blood. And then carbon dioxide, it hits at 45 inside the blood and then 40 in the alveoli, and so it has a gradient, not as big as the oxygen. We'll talk about why these are different in a second, but it moves down its gradient into the alveoli, which is 40, until it hits equilibrium. And so pretty much for here, it'll go from 104, it'll move down here until it equalizes 104, 104. Then from here, it'll equalize at 45. Or it's 40. I honestly don't know. I feel like it would be 45, but then it's exhaled. Yeah, probably. Yeah, I'm honestly not 100% sure. But the reason why, as you can see, there's a difference of about 60 for oxygen, and in CO2 we only have it being 5 millimeters of mercury. And the reason why we can still have an equal amount of exchange is because CO2 is a lot more soluble through the membrane than oxygen is. And so CO2 doesn't need as much of the gradient to move as much across, but O2, it's not as soluble across the membrane, but it still is soluble, but it needs a lot more of a gradient to move down to an equal amount of O2 or CO2. And then once this exchange happens, I kind of mentioned this before, we have these gradients to where it equalizes, I guess, is at 40. I think I got this from the book. So we have 40 in the alveoli and 40 in the blood, because the alveoli, remember, went and the CO2 went from the blood to the alveoli and equalized, and then oxygen went from the alveoli to the blood and equalized at 104. Then it's going to move down, but as it starts moving down, pretty soon it's going to drop to 95 to 100, and the reason why that is because there's kind of a mixture of deoxygenated blood still that's going to kind of carry its way through, so it's going to decrease that concentration a little bit. But then it's going to enter into the left atrium and then leave the left ventricle, and it's going to get pumped out. Down here we have some muscle tissue, let's say, and these are the gradients for the tissue. So in the tissue, we'll start with oxygen. So we have our blood oxygen, our partial pressure of blood, or of oxygen in the blood at 95. But then in kind of the interstitial space, we have the oxygen at 40. And then in the actual tissue, it's at 20. So it's just going to make its way down that gradient into the tissue. And then in here, something that happens is, I think it's glucose. It's like C6H12O6. And then you add that to oxygen. I think it's 6 oxygens. That's going to produce 6 waters and 6 CO2s. And so O2s, and it's also going to produce heat and ATP. But the important thing is that oxygen is being used, and it's inside the tissue. It's going to be one of the byproducts of it. It's going to be CO2. So that's why we end up with this high concentration of, or this 46 of CO2. And then now we're going to do CO2, or carbon dioxide. In the blood, it's 40. But here in the tissue, we have a 46. In the interstitial space, we have a 45, so it's going to move down its gradient. And then in the blood is the same thing as up top, but the opposite. It's going to move from 45 to 40. And then when that exchange happens, we're going to leave on the venous side. After it's done with that exchange of the tissue, where PO2 is going to be at 40, like we started with up here. And then our CO2 is going to be at 45 like we had up here, and it's just going to go through that cycle again. And this is all at resting. But yeah, that's how those pressure gradients, that's why they're so important. And we talked about the membranes and all that other good stuff, and so that's kind of how it ties into it and kind of a little bit of the bigger picture. Right here, drew this in a classroom. I was hoping to do it on the whiteboard, but a class started, and so I'm gonna I was planning on erasing stuff and redrawing it, so we'll see what I'll do here. But right now we're just gonna focus on this section. And so pretty much the important thing here, we just talked about these pressure gradients. And so we had oxygen, and I'm not going to use the exact numbers because it's not super important right now, but we know we have a gradient, a pressure gradient for oxygen to go in, and a pressure gradient for CO2 to move out. So this is deoxygenated blood comes in. It's in the T state. It's called deoxyhemoglobin. T state stands for tent state. And we talked about this in class, and I can't remember the exact details, but pretty much there's a conformational change on the hemoglobin where it hides the iron, and the iron is what attaches to the CO2. And so if that iron's hidden, CO2 is not going to be able to attach. So there's going to be a low affinity for O2. Sorry, I was meaning O2 this whole time when there's that iron lets O2, oxygen, attach. And so when that iron's hidden in the tent state, the affinity for O2 is going to go down. And then with that, kind of the hemoglobin is going to be more available to CO2 to attach. Only a little bit of CO2 attaches, but it does, but also hydrogen's attached to the hemoglobin. And then also we have 2,3 BPG, which also attaches to the hemoglobin, and that favors the T state. It wants to help keep it in the T state. So what happens here is we have this deoxygenated blood that comes back, and we have a red blood cell with a deoxyhemoglobin, and so in T state. And this is our alpha chain, our beta chains, and these have a little bit of a negative charge. They're like amino acids, and these amino acids have a little bit of a negative charge, so they're going to have hydrogens that are going to attach to them. And also, I can't remember exactly how, but with the makeup of CO2 in the blood, we talked about this a little bit when we talked about hemoglobin, I think during the cardiovascular unit, but 20% of the hemoglobin, or 20% of the CO2 actually attaches to the hemoglobin, so not a lot. So the rest of it is dissolved in the blood. That's about 2 to 10%. That leaves about 70% left over, and the extra 70% is hidden in bicarbonate. And we'll talk about how that gets changed back into CO2 and how that can then be kind of offloaded and go down its gradient into the alveoli. But what happens here, I guess let's just go right into how this works. So we obviously have a large gradient for CO2 to be offloaded and go into the alveoli. But up here, actually, let's start with oxygen. So oxygen, I'm going to draw it in blue. There's a huge gradient for oxygen to come in. So oxygen, even though it's not really invited to come on to the hemoglobin, there's still one on there, but it's gonna, since there's so much, like such a high concentration, it's gonna make its way onto one of these O2s. And I already drew one right there. I'll draw it again. But something, and by the way, this whole diagram right here, I got from Ninja Nerd, and so don't want to take credit for his amazing work. But let's see here. Yeah, so O2, I can't remember what it's called, but it's called like positive something. But pretty much what it is, it's like, okay, when oxygen starts binding on, it becomes a lot easier for more oxygen to bind on. So once you get one oxygen, two oxygens, then it's really easy for the third and fourth oxygen to then bind on to the hemoglobin. And the way he explained it on his video is, let's say, kind of have these 1, 2, 3, 4. Kind of have these 4 binding sites for oxygen. We started out having this first one on there. And then because we have this huge gradient of O2 coming in, we have our second oxygen kind of just force its way on, even though it's not super invited, it's going to kind of force its way on there. But then when that happens, I gotta turn it to the standard erase. That's then going to create a lot bigger of a binding site for the next two. And so you can kind of imagine these bigger binding sites just making it easier for oxygen to bind. So then we're going to have oxygen to bind to here. And then because the third one bound, that fourth binding site's going to be even bigger. And so I'm sure this is not how it actually works, but just kind of teaching the principle that when one oxygen bonds, it makes it easier for the following oxygens. And then as each one gets added to, it makes it easier and easier for the ones following. Then obviously we hit 4 and it's kind of maxed out. So we get all of our O2s, and trying to remember what exactly happens. I know there's kind of a few things that can happen, but I know one of the things is this 2,3 BPG. You can't see it super well, but that's what's right here in red. Kind of bubble around it. And what's happening there is this guy really favors the T state. But when we have oxygen, there's these positive charges, and 2,3 BPG I'm pretty sure is negative, and so it wants to attach there. But when we have oxygen come on, it kind of blocks off this this connecting point for that, and it kind of blocks away or hides those positive charges. So BP3 kind of gets knocked off. Then once we lose 2,3 BPG, I think it kind of just loses the, well, I think too, I'm just trying to think where this starts, but it might start where we have this gradient for CO2, so this CO2 just kind of hops off and joins, and then this hydrogen is going to hop off as well to help make CO2. And so maybe it starts out with these guys hopping off of the chains, and that's what causes the dissociation of 2,3 BPG, and maybe that's what allows the oxygen to kind of hop on. I can't remember the exact cascade of it all and how the intrinsic, not intrinsic, but the exact details, but this is semi kind of what's going on. And so I'll just jump over to the CO2 getting, so we talked about the CO2 right here, the 20% is going to hop off and diffuse through. And then this last part, which is important, is we said we had this 70% hidden kind of in this bicarbonate. What's going to happen is we have a transporter that's going to let bicarbonate enter. And bicarbonate's negative, and if we have a bunch of bicarbonate coming in, it's going to make the red blood cell negative. We don't want that, so it's going to be exchanged for chloride to equalize that, to keep it from becoming too negative. But then we talked about CO2 is going to kind of jump off when it goes through this kind of conformational physical change. Part of what happens is this H plus right here. I don't know what just happened. This H plus right here is going to hop off of the chain, and he's going to join up with bicarbonate. And if you remember, we talked about, we know what happens here. We talked about this in the last video with the kidneys, but H plus and HCO3 is going to go through the carbonic anhydrase. That enzyme is going to kind of speed up this reaction, and it's going to create, I think it creates H2, I can't remember, or whatever. But in the end, it's going to make H2O plus CO2. So that's how we convert the rest of our CO2, at least from that 70, and allow it to diffuse through. Then on the outside, it kind of goes through the same thing. At least in the Ninja Nerd video, it didn't say there's carbonic anhydrase, but it just said kind of naturally will convert once you get, because we'll turn into something else, I can't remember, but pretty much it's going to dissolve, but then it's going to be put back together, and it's going to be able to diffuse with all that. So that's kind of how it happens. That is how it happens. And once this happens, once we have the carbon dioxide leave, we and the hydrogens hop off, and this 2,3 BPG hops off. It changes its state into the R state. And the R state is the relaxed state, and that's when the iron can be exposed. And I should read it in the book about how this happens, because I bet it's pretty important to this process, how I was a little confused. But the iron becomes exposed, and the iron is what the oxygen attaches to. So now oxygen has a higher affinity, can attach, and then without the 2,3 BPG, CO2 and hydrogen lose their affinity, and yeah, there's no 2, BP3. So this is in the R state. And this effect right here is called a Haldane effect. And pretty much what it is, simply, Ninja Nerd explained it really well. It's O2 loading to hemoglobin. That's what we saw. And then it's CO2 offloading from the hemoglobin, which we saw there. And we saw where it comes from, these different areas, from bicarbonate, from being attached to the amino acid and being dissolved in the blood. So this last part, I guess not the last, but this other part, and this is kind of what our, once we, I know it's kind of dirty over here, but this is like our R state hemoglobin. As you can see, it has its O2s. Doesn't have carbon dioxide, doesn't have the hydrogens. But up here we have some tissue, and we're going to show how this exchange happens from when we get to the tissue side of things. And so we talked about over here, we kind of just went over this part where this exchange happens up here, but now we're going to talk about how it happens at this tissue side. And so we have our tissue, we have our capillary, and what's going to happen is, we talked about our pressures. We know we have a low concentration of O2 in here. So O2 is going to want to move down its gradient to the tissue. And because O2, I have the equation written up here, it's reacting with glucose, it's going to give us 6 CO2s and 6 waters, ATP and heat. But it's going to produce a good amount of, I think this might be 6 O2s, I'm not 100% sure. But it's going to give us a good amount of CO2s, and so now we have a lot of CO2s. And remember here we only have 40 millimeters of mercury, so it's going to want to make CO2 come in. So the way this happens, maybe I should just look in the book real quick. I don't know, let's look real quick. Let's see. I want to look at this offloading. Here it kind of is. What I'm kind of looking for is what kind of starts this cascade. It's okay. But pretty much what happens is we have a high gradient for oxygen to move its way down. And I don't know if the CO2 comes in and it attaches. And those hydrogens come in and they attach. And I think they might expose this site to where we can have that 2,3 BPG come in. And I don't know if the actual change happens when this binds, but we talked about how it goes from R state to T state, and then those irons become hidden through that little transformation. And when it becomes hidden, then it can leave those. Then it can leave those, or let those oxygens leave. And so, not 100% sure if that's the process, but it's something like that. And so, like we talked about, oxygen is going to come in, CO2 is going to come down, and about, I think it was 2 to 10% is in the blood, dissolved in the blood, about, I think, 20% here on the actual hemoglobin, and then we have the other, like 70% here hidden in bicarbonate in the blood. And, but that's actually not how it happens, sorry. Well, that is how it happens, but how it gets there is CO2 will diffuse, but also continue to diffuse into here. And we have CO2, but also inside of the hemoglobin, we have lots of water. So these two pals are going to come in, go through bicarbonate, or go through carbonic anhydrase, and they're going to produce hydrogen plus, which can then go on to here. And then it's also going to produce our HCO3. And then again, he's going to leave, but how does he do it? If he leaves too much, we're going to lose too many negatives, and that's going to cause the cell to become negative, and so we have chlorides come in to even that out. And again, this is now it's in the T state. And so this is the Bohr effect. And it's O2 offloading, which we saw, and CO2 onloading. And yeah, so we have the T state, the 10th state where the ions are blocked, and we have the R state where they're exposed and they're letting oxygen come on. And over here is a graph. I can't remember what the name of it is. Let's look on here. It's the hemoglobin dissociation curve graph. And as you can see, it looks like that. And kind of the gist of it, I feel like it's kind of more complicated than it needed to be, but it's kind of hard to understand. But this is kind of where the lungs, when it enters the lungs, we're at, remember that 104? That's kind of where we're at with the lungs. I don't know if you remember, because what this is saying is it's a hemoglobin saturation percentage on this side. So it's like the percent of oxygen that's on the hemoglobin, I think is what it is. Or I can't remember, but it's like the hemoglobin saturation percentage, how much of it's saturated with oxygen. And then down here is the pressure of oxygen. So over here, remember we'll just go over here, we have 104 with in our lungs once the exchange happens. But then down in the tissues, we have it at 40. And so with this, we're at 104 with the lungs. Then here it's like at the tissue, at 40. And so pretty much kind of what it's saying is we start out at like around, I drew it a little off, but kind of start out with about 98% saturation, that 104. And the thing doesn't start curving. I didn't draw it the best, but usually around, I think it's like around 60. It doesn't start curving down a ton. And so if we have the pressure of O2 about 100 to 60 or 70, I don't know, it's not going to make that much a difference. We might go from like 98 to 93 or something like that, but we're still at a high saturation percentage. But then if we start moving down kind of below 50, we start losing oxygen really quick. Our saturation goes down really quick. And so this is kind of the offloading where we see oxygen offload into the tissues. But right here, what we want to see is we want to look at how this matches up here. And once it hits the line, I drew it a little off, but I think it's supposed to be around 70. But as you can see from when we got oxygen, and we go down to the tissues, we offloaded about 28%. But if we're exercising, again, I draw a little off, but I think usually it's like supposed to be a little higher. But if you're exercising, you're going through a lot more oxygen, burning or producing a lot more CO2. So your saturation difference is going to be a lot different from when it goes from the lungs to the tissues. But an important thing is this graph kind of shifts. If it shifts to the right, it just means it kind of favors the, let me think. It favors the Haldane effect, I believe. No, sorry, maybe it's the Bohr effect. I think it favors the Bohr effect with when it goes to the right. And that's decreasing pH, creating more hydrogens, it's increasing temperature. Because again, heat can come and heat that's produced from exercise, it can come and break off these oxygens. But so increased temp can do that, increase offloading. CO2, if we increase CO2, if you remember our equation, if we increase CO2, it's going to push it more to the right, which is going to produce more hydrogens, contributes to that. And then also it's going to increase 2,3-BPG because it increases production of 2,3-BPG during hypoxia. If we go to the left, we're going to have an increase of pH, so less hydrogens, decrease of temperature, less heat breaking the O2 bonds to the hemoglobin, less CO2, which is going to cause the equation to move to the left towards the product side, which is going to decrease hydrogens. And then we're not in hypoxia, so we don't have a lot of BPG being produced. So, yeah, that's the final stuff of the lungs. Lungs is honestly super cool to me. Lots of cool stuff, very interesting, and honestly a lot easier than the kidneys as well. So, I'll have to look and kind of see the details of this whole process and kind of the chronological order and the cause and effect of things, but kind of covered mostly the important stuff. And this thing has always been a little confusing to me, but hopefully we got the gist of it down. But yeah, that's the last part of question 2 for Unit 4.